The number 38 sitting on a page tells you nothing. It's raw, unprocessed, and completely devoid of context. In computer science, we call this dumb and totally ambiguous, or data. Pass that number through a diagnostic process, attach it to a patient, and you get a fever. It becomes interpreted neatly for operations, INFO. Information is just data that has been given a job. To store that raw 38, the computer's hardware needs specific instructions. A data type acts as a low-level classification rule. Declaring the number as an integer explicitly tells the compiler to carve out exactly 4 bytes of physical memory to hold those bits. As programs scale, managing individual bytes becomes impossible. We need a conceptual layer to define what operations are allowed without worrying about how they actually work. An abstract data type, or ADT, is a theoretical contract. When you press volume up on a remote, you are executing an operation defined by the ADT. The internal circuit board is completely hidden from you. While the ADT writes the contract, a data structure is the physical employee that actually does the work. It is the concrete, memory-level implementation, like an array or a linked list, that fulfills the operations the ADT promised. Nicholas Wirth summarized this relationship into a famous equation: data structure plus algorithm equals program. You can write a brilliant search algorithm, but if you apply it to a million scattered books, finding one title will take hours. Organize those same books alphabetically on shelves, a physical data structure, and the exact same search takes seconds. Organization dictates efficiency. We map these organizational strategies on a rigid classification tree. The first split separates primitive structures, the basic integers, floats, and characters hardwired into the machine, from non-primitive structures, which are complex collections built out of those primitive blocks. Those complex, non-primitive structures divide into 2 categories based on their relationship mapping. Linear structures arrange data sequentially, where each element sits right next to the previous one. Non-linear structures break that single path, connecting elements into multi-level hierarchies or complex networks. This split creates a frequent exam trap. Because stacks and queues use specific access rules, like last in, first out, students often assume they are nonlinear. They are not. A stack of plates is still a sequential line going perfectly vertical. Remember the acronym SLAT. Stacks, linked lists, arrays, and queues are always linear. Internalizing this hierarchy provides a mental map for categorization. It ensures you can correctly identify whether a structure is primitive or derived when faced with conceptual exam questions. Once the data is physically organized, you need logic to manipulate it. An algorithm is a finite, well-defined sequence of instructions. A valid algorithm must satisfy 5 strict properties: finiteness, meaning it eventually stops, defined inputs and outputs, and steps that possess both regularity and definiteness, meaning every single action is unambiguous and actually executable. We visualize these steps using standard flowchart symbols. Ovals mark the start and end, rectangles process data, and parallelograms handle inputs. A common error on multiple choice tests is using a rectangle for a true or false branch. Always use a diamond for a decision. To evaluate an algorithm's efficiency, we analyze time complexity. We do not measure this with a stopwatch. Hardware speeds vary drastically. Instead, time complexity measures the mathematical growth rate of basic operations relative to the input size, denoted as n. Space complexity works on the exact same logic, measuring the total memory consumed. A common mistake here is counting only the storage required for the input data. You must also calculate the auxiliary space, the temporary variables, and the hidden recursive call stacks generated during computation. Let's count operations. If an outer loop runs n times, and an inner loop also runs n times per outer iteration, you multiply them. The algorithm executes n-squared operations. This geometric scaling forces us to use formal asymptotic limits to understand worst-case scenarios. This graph tracks an algorithm's operation count as the input size approaches infinity. Big O notation establishes the ceiling. It proves the worst-case scenario, guaranteeing your algorithm will grow no faster than the upper curve. Big Omega provides the floor, defining the best-case lower bound your operation count will never drop below. When an algorithm's growth is sandwiched so tightly that the upper Big O bound and the lower Big Omega bound are identical, we achieve theta. Theta represents the exact tight bound. We also use small o and small omega to represent strict, absolute limits where the growth curves can never intersect. Let's prove a function is big O of n. We need to show that 3n plus 5 is less than or equal to a constant c multiplied by n. If we test c equals 8, the inequality simplifies to 5 is less than or equal to 5n. This statement holds perfectly true for any input n that is greater than or equal to 1. We have our constants, c equals 8 and n0 equals 1. Pause the video and try to prove that 2n squared plus 3n plus 1 is big O of n squared. By dividing the entire polynomial by n squared, the lower order fractions approach 0 as n grows. This leaves us with 2 plus 3 plus 1, which equals 6. Setting c to 6 and n0 to 1 formally validates the bound. Deriving these bounds involve 3 consistent rules. Drop all constants, drop all lower order terms, and multiply nested loops. If you have 5n squared plus 100n, the constants and the linear n become statistically invisible at scale. The algorithm is simply n squared. Exam graders actively look for 3 mechanical errors. First, failing to simplify. O of n squared plus n squared is just O of n squared. You must drop the implied constant. Second, treating exponential bases like constants. O of 2 to the n is absolutely not equal to O of n. Third, assuming the best case is always O of 1. The best case depends strictly on the exact input array, not a hard-coded rule. This timeline ranks the complete growth rate hierarchy some constant time up to the unusable factorial time. Memorize the order with this phrase: every good student learns numerical concepts quickly, exponentially faster. E is O of 1, G is log n, S is square root, and so on. When answering a 5-mark asymptotic notation question, definitions alone earn partial credit. To secure maximum points, hit all 3 requirements. Write the formal mathematical inequality, provide the limit equivalent, and execute a brief algebraic proof using exact c and n0 variables. These 3 layers work in tandem. Abstract data types define the operations, data structures organize the memory, and asymptotic math predicts how those choices perform as the data grows.
Every sequence of data in a modern program relies on a rigid grid structure. These non-restricted linear lists are the building blocks for every complex system you will encounter, from databases to game engines. Inside a computer's RAM, data is just a sequence of electrical charges with no inherent meaning. To make those numbers useful, we apply structural rules. Data becomes information only when it is bound by a specific organization. This blueprint represents an abstract data type, or ADT. It is a mathematical model that defines what a list can do, like insert or retrieve, without specifying the code used to perform those actions. To implement this ADT, we choose between 2 physical layouts. Arrays use rigid, contiguous blocks of memory, while linked lists utilize dynamic, scattered addresses connected by pointers. Understanding these structures requires shifting focus from the abstract logic of programming to the physical geometry of memory. We have to map exactly how data is laid out on the hardware. Arrays allow for O1 direct access because their memory blocks are physically adjacent. If you know where the first element is, you know where every other element must be. The computer finds any specific element by taking the base address and adding the product of the index and the word size. However, computer RAM is strictly one-dimensional. It is a single, flat line of cells. This means that multidimensional arrays, like 2D grids or 3D cubes, are mathematical illusions that the hardware must flatten. Here, a 2D grid unwinds into a single tape using row major order, reading left to right, then down. To find A23, base 1000, 2 by ties, the computer skips the first 2 rows, 10 elements, and the first 3 columns of the third row, landing exactly on address 1026. The alternative is column major order, where the computer reads top to bottom down a column before moving to the next. The column major formula is a frequent source of error. Looking at the calculation here, you can see that the column index j must be multiplied by m, the number of rows, to correctly jump across the memory layout. Because array access is a mathematical derivation, any error in mapping this 1D illusion leads to the retrieval of the wrong data block. A matrix is considered sparse if non-zero elements make up less than 1/3 of the total dataset.
Storing thousands of zeros in a standard array creates an O of m times n memory overhead, which quickly exhausts available RAM in large-scale applications. Watch zeros fade from this 4x5 grid. The triple array conversion maps only the row, column, and value of remaining elements into a compact 3-column format. Index 0 is reserved for metadata, defining the original matrice's dimensions and non-zero count to interpret the data correctly. Transposing this matrix requires swapping the row and column values for every entry in the triplet array. Once the values are swapped, the array must be resorted by the new row index to ensure the matrix remains in a valid, traversable order. This conversion shifts space complexity to a dynamic O of k equation. Efficiency here is determined by the structural layout, not the raw size of the grid. Notice how these independent nodes connect via directed light. Linked lists solve the contiguous memory problem by allowing data to be allocated anywhere in RAM, as long as each node knows where the next one is located. While arrays require an O of n shift to insert an element at the front, linked lists complete this task in O of 1 time by simply updating a single pointer. The singly linked list is the basic unit of this architecture. Each node holds data and one forward pointer, which terminates at a null value to signal the end of the chain. This node belongs to a doubly linked list. By adding a previous pointer, we enable bidirectional traversal. If you have the node's address, you can delete it in O of 1 time, because the node already knows the addresses of its neighbors. A circular linked list routes the final node back to the head. This removes the null terminator entirely, creating a continuous loop. Traversal in a circular list requires a specific condition. Using a standard null check will result in an infinite loop. Instead, the loop must break when the next pointer matches the head address. Choosing a linked list trades the direct mathematical access of arrays for physical memory flexibility. The engineer must explicitly define every connection between data points. High-degree equations like x to the power of 100 are highly sparse. Storing these in a standard array would leave 99 empty slots for every active term. A linked list stores only the non-zero terms. Each node contains a coefficient and an exponent, skipping the empty powers to save significant memory. Adding these polynomials involves comparing exponents. If they match, the coefficients are added. If they differ, the term with the higher exponent is moved into the result list. By mapping mathematical equations to these pointer nodes, computer algebra systems can process complex symbolic math without exhausting memory. Manipulating pointers requires precise execution. Even small errors in how nodes are linked can cause a program to crash. Forgetting to check if a list is empty before a deletion operation will cause a segmentation fault, as the program attempts to access a memory address that does not exist. In this split screen, you see a memory leak. When an unlinked node is not freed by the programmer, that memory remains occupied and permanently unusable by the rest of the system. In doubly linked lists, a common error is updating the next pointer while forgetting to update the previous pointer, breaking the list's bidirectional integrity. Pointer bugs represent a disconnect between the logic of the code and the physical arrangement of the memory addresses. To conclude, let's consolidate the core mechanics of this module. Always distinguish between the ADT and its implementation. The ADT is the theoretical blueprint, while the array or linked list is the physical execution. The CARD mnemonic summarizes the two paths. Arrays provide contiguous memory and random access. Linked lists offer arbitrary memory and dynamic sizing. On this cheat sheet, notice the difference in 2D address formulas. Row major uses the column count, n, while column major uses the row count, m. The linked list hierarchy ranges from singly and doubly linked to circular and circular doubly linked. Each tier adds specific features like reverse pointers or wraparound loops. Sparse matrices use the 3k plus 3 formula for triplet storage, where k is the number of non-zero elements, and the extra 3 values store the essential metadata. Proficiency in data structures involves looking past the syntax of a programming language to visualize the movement of data through physical memory. Internalizing this geometry is the difference between a coder who follows instructions and an engineer who designs the architecture of a system. We take a chaotic, unstructured block of raw computer memory and enforce strict physical boundaries to make it predictable. Mastering restricted linear data structures involves tracking pointers and understanding exactly how they limit access to memory. This table outlines 3 structural categories based on their entry and exit points. A stack has exactly 1 active end, a queue has 2, and a DQ provides access at both sides. To navigate these structures, we isolate the active ends. For stacks, that is the top pointer. For queues, it is the movement of both the front and rear pointers. Losing track of these pointers creates specific edge cases, memory leaks caused by phantom overflows, or mathematically reversed postfix evaluations. Writing algorithms that execute safely requires knowing exactly where these pointers sit and precisely when they hit their absolute physical limits. A stack restricts all insertion and deletion to one side, enforcing a last-in, first-out, or LIFO principle. In the lassie-in-fridge-out analogy, the last item placed inside is the first one you extract. Array implementations restrict the stack to a fixed maximum size, creating a risk of overflow. Conversely, a linked list allows the stack to grow dynamically until the system's memory is fully exhausted. Watch the top index variable. To push an item, top must increment forward by 1 before the data occupies the slot. To pop, the data is removed and top immediately decrements. This LIFO order allows computers to translate human-readable math into logic. In an infix to postfix conversion, the stack holds operators like plus or multiply, delaying their execution until their operands are processed. Precedence rules dictate when these operators leave the stack. An incoming operator kicks out any existing operator of higher or equal priority, ensuring multiplication happens before addition. Because the stack inherently manages this hierarchy, the computer can process complex expressions in a single pass without needing parentheses to define the order. Evaluating a postfix expression requires reading left to right, push numbers onto the stack as they appear, and pop exactly 2 numbers the moment an operator is encountered. At the subtraction step, the minus operator triggers a double pop of the top values, 5 and 6. Because of LIFO, the first value out, the 5, becomes the right side operand. The second value out, the 6, becomes the left side operand. The check is pop B, then A. The mathematical result is A operator B. Treating the stack output chronologically results in subtracting 6 from 5. This specific LIFO reversal is why logically sound code can yield mathematically incorrect output. Recursion applies this stack logic to function calls. A recursive function relies on 2 parts, a recursive case that calls itself with a smaller input, and a base case that dictates the termination condition. Look at the system's call stack. In the winding phase, factorial 3 pushes distinct memory frames downward. Hitting the base case of factorial 0, the stack strikes a solid floor. The unwinding phase pushes resolved values back up, frame by frame. Without a base case floor, the function continually calls itself. The operating system exhausts its memory allocating new frames, resulting in a stack overflow error. We can optimize this using tail recursion. If the recursive call is the absolute final action in the function, with no pending math afterward, compilers can reuse the current frame rather than generating new ones. Recursion is the operating system executing a rigorously managed LIFO stack on the programmer's behalf. We can test the depth of the call stack with the Tower of Hanoi puzzle. Moving n disks from a source to a destination requires never placing a larger disk on a smaller one. Shifting n-1 disks to the auxiliary peg, moving the largest to the destination, then moving the pile again adds execution frames. Tracing this reveals the minimum moves, 2 to the power of n minus 1, yielding a time complexity of O of 2 to the n. A deeply nested physical puzzle is instantly resolved by leveraging the predictable depth of the call stack. Moving from the single-ended stack to a queue requires splitting our pointers. We restrict insertions to the rear and deletions to the front to enforce a first-in, first-out model. This dual pointer array has a structural flaw. Pushing data advances the rear pointer to the max index. Dequeuing advances the front pointer forward. Observe the empty space left behind. Adding another item is rejected because rear hit the physical limit. This is a phantom overflow. The array has physical space at the front, but linear pointers cannot reverse direction to reclaim it. Linear arrays degrade over time because the physical model fails unless we apply modular arithmetic to the pointers. The circular queue solves the phantom overflow by treating the array as a ring. The modulo operator forces the rear pointer to wrap back to index 0, but mapping to a circle requires a sacrifice. One slot remains permanently empty to distinguish full from empty. The boundary condition becomes rear plus 1 modulo max equals front. Modular arithmetic allows the queue to reclaim abandoned memory slots, bending linear memory into a continuous logical loop. Controlling both ends of a linear array allows us to construct a double end of queue, or DQ. It supports insertions and deletions at both the front and rear ends. We can lock permissions to create variants. An input-restricted DQ limits insertion to the rear. An output-restricted DQ limits deletion to the front. By closing specific doors, a single DQ can simulate either the LIFO behavior of a stack or the FIFO scheduling of a queue. The DQ acts as the parent structure, demonstrating that these architectures are varying degrees of restricted access to the same linear memory. Mastering this material requires understanding the precise boundary conditions for each implementation. We can distill these rules into a logic matrix. An array stack is empty when top is -1 and full at max -1. A circular queue relies on modular arithmetic to detect a full state. Linked list variants track empty states via a null pointer. While they avoid structural overflows, they sacrifice the cache-friendly speed of contiguous array memory. Keep the core edge cases in mind. Postfix subtraction requires popping operand B, then operand A, and the circular queue always reserves one memory slot. Success in these systems is achieved by tracking active pointers and anticipating the exact moment they hit the edge of their physical reality. Most of the data structures we've used so far have been linear, but as we move into trees and graphs, we have to manage data that branches and loops. This module is a significant part of the curriculum and focuses on how these structures are built and traversed. A tree is a hierarchy of nodes where no cycles exist. When measuring its dimensions, pay attention to the direction. Height is measured starting from the bottom leaves and moving up toward the root. Depth is measured from the root moving down. To find a level of a node, you take its depth and add 1. Exams frequently test the distinction between full and complete binary trees. In a full tree, every node must have either 0 or exactly 2 children. A complete tree is different. It requires every level to be filled from left to right, ensuring the nodes are packed as tightly as possible. Binary search trees, or BSTs, follow a strict ordering. All values in the left subtree are smaller than the root, and all values in the right are larger. To remember the traversal orders, use the PIP mnemonic. Pre-order handles the root first, in-order puts it in the middle, and post-order visits it last. Because of that specific left-root-right ordering, an in-order traversal of a BST will produce a sequence of values in perfectly sorted order. This property is often the starting point for more complex tree problems. If a BST becomes heavily skewed to one side, its performance drops. AVL trees prevent this by calculating a balance factor for every node, which is the height of the left subtree minus the height of the right. If that factor reaches plus or minus 2, the tree is imbalanced and must be rotated. In this left-left imbalance, 30, 20, and 10 form a line to the left. Node 30 has a balance factor of plus 2. To fix this, we perform a single right rotation. Node 20 is pulled up to the root, which moves 30 down to become its right child. We see the opposite in a right-right imbalance. With 10, 20, and 30 forming a line to the right, node 10 hits a balance factor of -2. A single left rotation pulls 20 up to the root and moves 10 to the left. If the nodes form a dogleg shape, like 30, 10, and 20, we need a double rotation. This is a left-right case. First, we perform a left rotation at the child node to straighten the path into a line. Then we apply a right rotation at the root to bring 20 to the top. For a right-left dogleg, 10, 30, 20, the process is mirrored. We rotate node 30 to the right to create a straight line, then rotate node 10 to the left to pull 20 into the root position. To identify the correct rotation quickly, find the node where the balance factor has failed.
Trace the path down to its grandchild and use the direction of that path, LL, RR, LR, or RL, to choose your rotation. While binary trees are limited to 2 children, B-trees are M-way search trees used in databases. In a B-trees of order M, each node can have up to M children and hold M-1 keys. When a node exceeds its capacity, it must split. In a B-tree, the median value, 10 in this example, is pushed up to become a parent node, while the remaining values are divided into new left and right children. A common variant is the B+ tree. This structure changes how data is organized by ensuring that all actual records are stored only at the leaf level. When a B+ tree leaf splits, the median value is copied to the parent to act as a guide, but it also remains in the leaf to preserve the data. This allows all the leaf nodes to be linked together, providing fast sequential access to the entire dataset. Because every piece of data is in a leaf and those leaves are linked, B+ trees are the standard choice for database indexing, where range queries and sequential scans are common. A heap is a complete binary tree that we can store efficiently in an array. By using the index I, we can find any node's children at 2i and 2i plus 1 without needing pointers. To build a max heap, we start from the last internal node, found at index n/2, and work backward to the root. At each step, we sift down by comparing the node with its children and swapping them if the heap property is violated. If we look at the workload for this process, the bottom level contains roughly half of all nodes, but they require 0 work because they cannot sift down further. As we move up the tree, the number of nodes decreases significantly, which offsets the longer distances they might have to travel. Because of this balance, building a heap takes O of n time. Once the heap is established, we can remove the maximum element and restore the structure in logarithmic time. This efficiency is why heaps are used to power priority queues in operating systems for task scheduling. Graphs are collections of vertices and edges that can represent complex networks. To explore them, we use depth-first search, which uses a stack to go as deep as possible, or breadth-first search, which uses a queue to explore neighbors level by level. Let's trace a depth-first search. Starting from node 1, the path moves to the first neighbor, then immediately to that neighbor's neighbor, continuing until it can't go any deeper. Watch the path here as it connects back to node 1. Since node 1 is an ancestor of our current position in the traversal, this connection is classified as a back edge. Identifying a back edge is significant because it is the mathematical proof that the graph contains a cycle. We can combine these concepts into heap sort. First, we build a max heap. Then, we repeatedly swap the root with the last element in the array, shrink our boundary, and sift the new root down to maintain the heap until every element is in its sorted position. Heap sort runs in O of n log n time and is very space efficient because it sorts the array in place. However, unlike merge sort, it is not a stable sorting algorithm. This table summarizes the data structures used for each traversal and how to classify the different types of edges you'll encounter in graph problems. Here is a summary of the time complexities for the nonlinear structures we've covered. Reviewing these average and worst-case scenarios is essential for the MCQ portion of the exam. Finally, these formulas will help you calculate node properties and array indices quickly.
Algorithmic analysis requires looking past average case performance. To secure a score, you must navigate specific edge cases, hardware constraints, and the absolute limits of logical boundaries. Raw, unsorted data functions as noise. Without an underlying structure, any attempt to retrieve a specific record requires a brute force effort that scales poorly with volume. Sorting represents the essential computational investment. You expend resources to organize the set now to drastically reduce the cost of every future query. Once that order is established, searching transforms from a scan into a mathematical calculation used to pinpoint a specific target index. Hashing serves as the final optimization. By mapping keys directly to fixed-size indices, you bypass iterative searching entirely for direct data access. Computer science offers no universal best algorithm. Instead, it offers a trade-off matrix where every efficiency gain in one area creates a calculated compromise in another. Selecting the correct algorithm requires balancing two primary constraints: the limits of auxiliary memory and the preservation of relative order. An in-place sort operates within the bounds of the original array. It maintains an O1 space complexity, meaning it requires no significant additional RAM to reorganize the data. Stability preserves the original sequence of equal elements. If 3A precedes 3B, a stable sort ensures they remain in that exact sequence. An unstable algorithm disrupts this, swacking identical entries and destroying the original chronological context. These two variables, stability and space, are the primary indicators used to differentiate between algorithms that share the same asymptotic time complexity. The mnemonic BSIQMR categorizes the primary sorting tiers, while BIM identifies the three that guarantee stability: bubble, insertion, and merge sort. While bubble sort is generally inefficient at O of n squared, implementing a swapped flag allows the algorithm to terminate early if it detects the array is already organized, reaching O of n in its best case. Selection sort remains O of n squared across all cases, but it is mathematically unique in how it handles memory. It caps memory writes at a strict maximum of n-1 swaps. This makes selection sort the optimal choice for hardware with high-cost memory writes, such as flash memory, where the number of operations matters more than pure CPU cycles. Quicksort typically offers the fastest practical performance due to cache locality, but it contains a specific trigger that collapses its efficiency to O of n squared. This collapses when partitioning a sorted array with a boundary pivot, isolating one element per level into a deep, unbalanced tree. Merge sort avoids this by strictly halving the array during every step, guaranteeing O of n log n performance. However, merge sort is not an in-place algorithm. It requires an entirely separate auxiliary array of size n to execute the merge phase, doubling its memory footprint. Radix sort bypasses element comparisons entirely to achieve linear time, though it is strictly limited to fixed-width integers or strings, where it can sort by individual digits. Effective algorithm selection is rarely about average speed. It is driven by memory overhead, strict stability requirements, and the initial input state. Querying unsorted data begins with linear search, an O of n process that scans every element until the target is found. Optimize this at the hardware level using a sentinel. Placing the target key at the array's end ensures the loop always terminates naturally. This allows the processor to skip bounds checking on every iteration, cutting actual execution time in half while maintaining O of n complexity. Binary search improves this to O of log n by strictly halving the search space of a sorted array on every step. For any dataset of size n, the absolute maximum number of comparisons required is mathematically capped at the floor of log base 2 of n plus 1. Interpolation search goes further, using a formula to estimate the target's position based on the values at the low and high boundaries. This provides O of log n speeds on uniformly distributed data, but the performance collapses to a linear O of n if the data follows an exponential distribution. Effective search strategies require more than understanding asymptotic leaves. They require matching the algorithm to the specific distribution of the data. Hashing attempts to achieve an average O of 1 access time by mapping keys directly to indices within a fixed size table. The density of this table is defined by the load factor, the ratio of stored elements to the total number of available slots. As this factor rises, collisions become unavoidable. The pigeonhole principle dictates that when the number of keys exceeds the number of slots, multiple keys must occupy the same index. The hash function is critical. Using modulo 10 causes every key ending in 0 to collide at index 0, creating performance-degrading clusters. Shifting to a prime number divisor, like 13, forces keys to scatter uniformly across the entire index range, preventing this clustering. Open addressing resolves these collisions by probing for the next empty slot. Linear probing checks each subsequent index, but this often leads to primary clustering, where long blocks of filled slots slow down every operation. Quadratic probing uses squared increments to leap past these clusters. While this solves primary clustering, keys that share an initial hash will still follow the same path, creating secondary clustering. Double hashing provides the most effective resolution. It uses a second hash function to determine a unique step size for every key, ensuring that even keys that initially collide will diverge during the probing sequence. Genuine O of 1 access is only maintained through rigorous mathematical dispersion and a deterministic protocol for resolving collisions. This unified matrix maps the three pillars of the module. BSIQMR organizes sorting by complexity tiers, with BIM specifically identifying the stable options. The LSBI search progression tracks the shift from linear scans to distribution-aware formulas. The CLQD hashing hierarchy identifies collision resolution strategies, moving from external chaining to the optimized dispersion of double hashing. Across all three domains, the underlying data structure dictates the ultimate ceiling of algorithmic performance. For specific requirements, selection sort remains the only choice for minimizing total swaps, as it is capped at exactly n-1. Merge sort is the standard for linked lists because it processes data sequentially, avoiding the need for the random access indexing required by quicksort. The Sentinel search exists exclusively to optimize the loop by removing half of the required condition evaluations. And the primary risk of quicksort is applying it to already sorted data with a boundary pivot, which forces an ON² execution. To demonstrate full technical mastery, you must provide the formal definition, the algorithm itself, and a rigorous trace of the worst-case space and time bounds.